Okay, now it's time to begin tackling titration curves. So this is the beginning of section 19.2. I will try my best to go into as much detail as I can about these, but if you're confused, again, you can always go back and replay the video, or again, I highly encourage you to read your textbook about this. They have example problem 19.2 that I would highly suggest you work your way through and get some practice with these. Any of these techniques I'm going to show you, or the calculations I'm going to show you, apply for any specific type of titration for that type. So we're going to start with the easiest case, a strong acid titrated with a strong base. Before we get started, I just kind of want to remind you, we've done this in lab a little bit, but we need to remember that the equivalence point is the point at which the moles of acid equals the moles of base. And whether or not it's an acid being titrated with a base or a base being titrated with an acid, the equivalence point is always going to be the same. It's always going to be the point where the moles of acid equals the moles of base. And from there we can calculate the equivalence volume. Something to notice from the graph on the right is that at point C, that is our equivalence point in this case, for a strong acid, strong base titration, the equivalence point will always happen when the pH is 7. And we'll see that throughout this. So we're going to do 4 calculations. We're going to calculate the pH at point A before we've added any of our titrant. We're going to calculate the pH at point B at some point before the equivalence volume. Point C, we're going to calculate the pH at the equivalence point, and then point D, we're going to calculate what the pH would be after the equivalence point. These tend to get a little confusing with all the different reactions that are going on and having to try and memorize which reaction goes where. So again, I encourage you to reread the textbook on this and just always kind of take a step back and ask yourself, what is in the beaker? What reactions can I possibly have? What's going on in that beaker? So without any further ado, let's go ahead and get started. Part A, calculating the pH before we've added any of the strong base. So in your lab setup, this would be the strong acid would be in the flask down below the burette, and in the burette would be the strong base. So the pH of the strong acid before adding any strong base. So we're going to start with 40 milliliters of 0.100 molar HCl. It's our strong acid. And so the pH from that's pretty straightforward. If we just think of 0.011 or 0.111 molar HCl, that's going to dissociate completely into 0.100 molar HClO, H3O plus hydronium, and 0.100 molar, I guess I need another 0 in there, but it doesn't matter, 0.1000 molar Cl minus. And in this case, the chloride's not going to do anything, so we're just not going to worry about that at all. So our pH is only dependent on the hydronium ion concentration, so that's just the negative log of 0.100 molar, and we end up with a pH of 1. So first step, pretty straightforward. Now even though there's a ton of sig figs in the log term here, there are 4 sig figs in that log term. Let's see if I can change that back to black here. There we go. There are 4 sig figs in the log term. We're just going to, for most of our titration purposes, we're just going to round to 2 decimal places for our pH. So on to part B, after we've added some amount of strong base. So in this case, we're going to say the pH after adding 20 milliliters of 0.100 molar NaOH. So we need to find the number of moles of hydroxide added to the number of moles of H3O plus that were there. And the reason now we're switching to moles instead of concentration is that we've just added 20 milliliters to a 40 milliliter solution. So we're changing the volume. These things are getting slowly diluted as we go through this titration. So we need to figure out how many moles we had of each. So the initial moles of H3O plus is simply equal to the 40 milliliters, so 0.04 liters, times the 0.1 molar HCl gives us 0.00400 moles of HCl, or H3O+, dissociates completely. The initial moles of hydroxide, that's coming from the 0.020 liters, or 20 milliliters, of the 0.100 molar sodium hydroxide, which again dissociates completely, so we end up with 0.00200 moles of hydroxide. So again, this is where I always like to stop and ask myself what's in the flask. All we have is water, H3O+, OH-, and some sodium chloride, but the sodium chloride don't do anything, so the only reaction I have possible is between the strong acid H3O+ and OH-. So let's go ahead and write that reaction. That's just going to be H3O+ and OH- reacts completely to form 2 moles of H2O. So this is kind of a modified Rice table, but instead of equilibrium, that's supposed to be change. The change, instead of equilibrium, we're just going to call it the final, because it's not really at an equilibrium, it pretty much goes to completion. So initially, we had 0.00400 moles, and I'm going to write moles really tiny just to kind of remind myself that it's moles, not concentration, and 0.00200 moles of hydroxide. And the nice part is the water doesn't matter. So let's draw a little line here, kind of remind ourselves that's the final. The water doesn't matter, so we can kind of cross it out. So we look and we see we have 0.002 moles of hydroxide and 0.004 moles of the H3O+. So let's just write a little note. OH- is the limiting reactant. I can't spell today. OH- is the limiting reactant, which means we can only react that much. So we're going to react 0.00200 moles minus 0.00200 moles. Easy math is that that's a 0. And we have 0.00200 moles of H3O+ left over. So now we can go back and find the pH from the number of moles, but again we have to remember that we've changed the volume as well. So we can go back and calculate the concentration of H3O+. This is going to be the 0.00200 moles we have left over the new volume, which was 0.040 liters plus 0.02 liters, or 0.06 liters. So our H3O+ concentration is now repeating 0.0333333 molar. I'm just going to round it to 3 threes. So we take the negative log of that. The pH is going to be negative log of 0.0333. And our final pH is 1.48. So we've got the pH now. We're done with part B. We can move on to part C. So now we're going to be at the equivalence point. And so that means we've added 40 milliliters of 0.100 molar NaOH. And we can prove we're at the equivalence point by making sure the moles of acid and base are equal to each other. So if we remember from the first step, we had 40 milliliters of 0.100 molar HCl, and now we've added 40 milliliters of 0.100 molar NaOH. This means we have 0.00400 moles of H3O+, and this means we have 0.00400 moles of OH-, moles of acid equals moles of base. We are at the equivalence point. So let's just really quickly write the reaction for this. H3O+ plus OH-, 2 moles of H2O. forget about the water. We had 0.00400 moles and 0.00400 moles. They're both limiting. They're going to run out at the same time. So at the final end of the reaction, we have 0 moles of both of those. So again, we just go back and ask ourselves, what do we have in the beaker? Well, the only thing in the beaker is Na plus and Cl minus. Which they don't do anything to the pH. The only other thing in the beaker is H2O. And we know that water can auto-ionize in an equilibrium to form H3O plus and OH minus. So our pH is only dependent on that concentration of H3O plus there, which this auto-ionization has a Kw. If you remember the auto-ionization of water, the H3O plus concentration is just 1 times 10 to the negative 7th. So our pH is the negative log of that, and our pH is 7. So we've kind of proven there, again, what I've been saying is that the pH of a strong acid strong base is always 7 at the equivalence point. Always, always, always. Alright, part D, we're going to go past the equivalence point and continue adding some hydroxide. And so now let's say we've added 50 milliliters of the 0.100 molar NaOH. So again, let's calculate how many moles we had of each. Moles of H3O plus in the reaction at the very beginning, before we've done all this, we had 0.00400 moles of H3O plus. And now that we've added the 50 milliliters of the hydroxide, the moles of OH minus is going to be 0.100 molar times the 50 milliliters, turn that into liters, and we end up with 0.00500 moles of the hydroxide. So now the H3O plus is the limiting reactant. If we go back to our strong acid reaction, we had 0.400 moles of H3O plus and 0.0040500 moles of the hydroxide. So now we're going to run out of the H3O plus first. So that's the limiting reactant. So we can only react 0.004 moles. And we don't care about water. So that means at the end of all of this, after we've added the 50 milliliters, the strong acid reaction has happened. And at the very end of that, we have 0.00100 moles of hydroxide left over. So in order to get the pH, we need to turn that number of moles into a concentration and then calculate the pOH, and from there we can calculate the pH. The alternative is that you could calculate the H3O plus concentration from the OH concentration and then take the negative log of that. They both give you the same answer, pretty much the same number of steps. There's not a big difference. So first we need the concentration of OH minus. We have the number of moles. It was 0.10, oops, off by a factor of 10 there. 0.100 moles of hydroxide, and that's going to be over, so we had 0.040 liters of the strong acid, and we've added 0.50 liters of the strong base, so over 0.09 liters total. You run that math and you end up with 0.0111 molar hydroxide. We take the negative log of that. So our pOH is going to be the negative log of 0.0111. So our pOH is 1.95. Our pH is equal to 14 minus the pOH. Remember, pH plus pOH is equal to 14. So pH is 14 minus pOH, so our pH is equal to 14 minus 9.1, or 1.95, excuse me, and we end up with pH is equal to 12.05. And just a quick critical thinking check. That is very basic, and it should be, because we are essentially out of H3O+, and all we are adding is strong base hydroxide to the equation. So if we go back and look at point D, we are pretty much at the tall end of the pH scale. We should be in the basic region, and we are with that pH. So that's part one, the strong acid, strong base. I'm breaking this up into 3 parts, so the next one will be a weak acid with a strong base, part 2. That'll be in a separate video because these get fairly long, as you can see.